I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on heat transfers, heat engines, and the second law of thermodynamics. All right, in this video, we're going to talk about heat transfers for the first part, which we have three types: thermal conduction, convection, and radiation. So we're going to start with thermal conduction. Thermal conduction, also known just simply by conduction, this is an energy transfer through direct contact, and it has to have temperature differences for there to be an energy transfer. Common example of conduction is just a pot sitting on the stove. Maybe you're boiling water or warming up some soup. So that's the heat from the flame or the burner is in direct contact with the pan. So thermal conduction at the molecular level. We know that the cooler molecules don't move as fast as the hotter molecules based on their temperatures. And the hotter molecules have more kinetic energy, as we learned previously. So that means the faster molecules are going to collide with the slower molecules, and they transfer energy to the slower molecules, and that reduces the energy of the faster molecules through those collisions. This increase of the kinetic energy of the cooler molecules and increase the temperature until the thermal equilibrium has been reached. So the warmer molecules slow down, so they get cooler, and the cooler molecules get faster, so they warm up through those elastic collisions that occur at the molecular level. So thermal conduction is, we're going to calculate the rate of energy transfer because of thermal conduction. So let's take a cross-sectional area of a wall, say in your house. And we'll say that it has an area of A. The temperature on one side is TH and the temperature on the other side is TC. And that wall has a thickness of L. So here's all of those variables. And we're going to say that TH is greater than TC. So there's a hotter temperature on the left side of that wall than on the right side. So energy is going to flow from left to right through that wall. So what we know is that energy transfer, the rate is called power. And power is simply an energy transfer over time. And that energy transfer is going to be heat over time. So we're going to look at that rate of energy transfer, Q divided by delta T. So we know that from our previous videos that these variables, we know that the rate at which energy is transferred is going to be directly proportional to the change in temperature because heat's directly proportional to the change in temperature. Now, the rate at which energy is going to be transferred through that wall is also dependent on the area and the thickness. So the area, the bigger the area, the easier or the faster the rate of energy, and the slower if it's smaller. So that's going to be a direct relationship. Now, the thickness of the wall, the thicker it is, the rate to get through that wall is going to be smaller. So the thicker the wall is going to be an inverse relationship with the rate at which energy is transferred. Now, we can take any proportionality and we can multiply that proportionality by a constant, and that is going to make it an equality. So we're going to call that constant K, and that K value is actually called the thermal conductivity of that substance. And each substance has a different thermal conductivity value. So if we look at our variables and what each thing means, Q is the energy transferred in joules, delta T is going to be the time that's elapsed, K is the thermal conductivity, and that unit is joules per second meter degrees Celsius. We'll talk more about that in a little bit. A is the cross-sectional area of the surface in meters squared. Delta T is the temperature difference between the surfaces in degrees Celsius or Kelvin, since the change is going to be the same. And L is going to be the thickness of the object, or the wall in this case, measured in meters. So the thermal conductivity, so each substance has a different thermal conductivity value. The higher the value, the faster or the quicker the rate of energy is transferred. So that's called a conductor. A conductor has high value of thermal conductivity. So example would be metals. So like aluminum foil, heat transfers very quickly through aluminum foil because it's a metal and it has a very large thermal conductivity. An insulator has a low value of thermal conductivity, and examples of those would be gases or nonmetals such as plastics or any of the elements that we have in the top right of our periodic table. So what we're going to do in this slide is we're going to look at two cross-sectional areas of windows that have the same area and same thickness but one's a single pane window and one's a double pane. The double pane just means that there's air in between the two panes. And we're going to be asked which style of window is a better insulator. So what we're going to do is we're going to compare the thermal conductivity constant for the substances. So glass is zero point 0.8, so that means for the single pane, it's zero point 0.8 all the way through. For the double pane, we just have those two little sections that are zero point 0.8, so about a third or two-thirds the thickness of the single pane. But the thermal conductivity of air is 0.0234 joule per second meter degree Celsius, and that value is 34 times smaller, which means the rate of energy transfer is also 34 times smaller. So what that means is it's going to take a lot longer for that energy to transfer through the double pane window because of that thermal conductivity constant of air. Now, mostly single pane windows are about the same thickness as one of those panes in a double pane. So double pane windows are usually more expensive because they use more glass, but they are much better insulators than a single pane window. Another type of energy transfer is called convection. And convection is energy transferred through the movement of fluids. Remember, a fluid is a gas or a liquid. So let's look at that boiling pot of water that you had on the table. We have conduction at the contact point between the flame and the pan. But what's causing that water to boil faster is the process of convection. So the water warms up quicker at the bottom of the pan. And what happens is that water at the bottom of the pan then circulates to the top of the surface of the water, which then the cool water drops to the bottom. And these are what are known as convection currents. And that is the process of convection that helps water boil quicker than if just the water molecules had to heat up in layers. So the convection currents actually help the water to boil more quickly instead of just having to transfer all that energy through layers of water. So other examples of convection, you have a convection oven that uses a fan exhaust system to circulate warm air evenly to cook food, a campfire which has the energy transferring from the fire upward, causing that air to warm up so that warm air circulates upward. And then we also have the HVAC system in your house. So we have warm air being heated at the top, and then it sinks down and cool air goes to the return, and it keeps blowing through the heat vent to warm your house in the wintertime. Another form of energy transfer is radiation. So an example of radiation would be animals being kept warm under a heat lamp. So we know this is in conduction because this heat source is not in contact with the animals. So and the air has a very small thermal conductivity. We know this is not convection because convection currents actually would cause the warm air to rise and go above the heat lamp and not go down. So what's happening is that energy is radiating to keep the animals warm. So objects that radiate energy in the form of electromagnetic waves or light. So light is what's heating the animals in this case. Thermal vibrations in object molecules are responsible for the radiation, and this is what causes objects to glow. So example, the coils in a toaster or on an electric oven or heaters, things like that. So our energy transfer recap. We have three forms of energy transfer. We have conduction. So if we have a campfire and we put a metal rod, hold that metal rod in that fire, that it's in contact, the conduction, eventually that metal rod is going to heat all the way through and warm up. So remember that conduction means that there is contact between the objects, and that's what causes the energy transfer. And then convection, if we reach above the fire, we have warm air that's rising because the warm air is causing the fluid to circulate upward. That's energy transfer by the movement of a fluid, that's liquid or gas. And then lastly, we have radiation. So the light from that fire is also going to radiate outward towards our hands to keep our hands warm. So we can put our hands up. We don't have to put our hands above the fire. We can actually stand close to the fire, and that electromagnetic waves or light is what transfers the energy. In the second part of this, we're going to talk about heat engines, second law of thermodynamics, and entropy. So the second law of thermodynamics, there's a couple statements we're going to look at. There's no process that's possible whose sole result is the complete conversion of heat from a hot reservoir into mechanical work. And there's no process that's possible whose sole result is the transfer of heat from a cooler to a hotter body. So energy transfers from a hotter to a cooler substance unless we have some assistance. So a heat engine convert heat into useful work. They always have waste heat, and the efficiency can be used to tell how much heat is needed to produce a given amount of work. So heat transfer, so we have a heat source in a high temperature to low temperature. We know that heat's going to flow from the hot temperature to the cold temperature, and those heat energies would be equal. Now, if we put an engine in between, then what happens is the heat flows into that engine. It takes mechanical work out, and then the waste heat is transferred to the low temperature. So this is the process of transferring energy and using mechanical work. So QH equals QC plus W. So clarification, a heat engine is not something that produces heat. It uses heat to transfer from hot to cold and produces mechanical work in the process. So here's an application thinking about a piston in your car engine. So we transfer heat in, and that heat transferring in causes the internal energy of the gas to increase, creating a high pressure and temperature. So what happens in the next situation is that that piston gets forced outward. So that's the mechanical work that's produced by the heat. So the force that's exerted on the movable piston expands the piston. The gas pressure and temperature decrease during expansion. That means the volume increases. So three things are changing. And the internal energy, there is no change in internal energy. So that's an adiabatic process. And so this is an example of a quick, rapid change in volume. Then we have that heat is released out. That's the waste heat. And then it allows that piston to contract and be able to move a lot easier back to its original position. So this is an application of a heat engine where we have heat transferring in, causing mechanical work, and then the waste heat being transferred out. So a quick review of isothermal and adiabatic expansion. Isothermal expansion, remember, is an inverse relationship between pressure and volume, and an adiabatic expansion is a much quicker drop from an isothermal expansion where there's no heat loss, so the work is equal to the change in internal energy. So why is this important? Well, we're going to look at something called a Carnot engine. And what a Carnot engine was a theoretical engine that was developed by a French engineer and founder of thermodynamics, Sadi Carnot. The heat engine operates in an ideal reversible cycle that's called a Carnot cycle between two reservoirs in its most efficient engine possible. And when the second law of thermodynamics states that not all the supplied heat in a heat engine can be used to do work, the Carnot efficiency sets that limiting value on the fraction of the heat which can be used. So we're going to look at a Carnot cycle on a PV diagram. So we transfer heat in that causes that piston to have an isothermal expansion. Then we have an adiabatic expansion. From that process, we have an isothermal compression where the heat is transferred out. And then we have an adiabatic compression as well. And the overall area of that curve is the work that's transferred to that piston out of the system. So we know that's an overall negative amount of work, but the heat is equal to the cool heat plus the work, and that's a negative work that's done on the gas. So the efficiency can be calculated simply by doing the work divided by the warm heat, and that is the cool heat is the waste heat. So if we know the work divided by QH, we know that work is QH minus QC. And if we know Q equals MC delta T, well, that means if we substitute all of those in, we're just going to end up using the hot temperature minus the cold temperature divided by the hot temperature, and that's known as the Carnot efficiency. And to get a percentage, we would just multiply that number by 100% to make it a percentage. So let's talk about refrigerators and air conditioners that actually cause the heat to flow the opposite way. And what is needed is something to provide work called a thermal pump. So what happens is we take that cool heat, we move it through the thermal pump, and it transfers that heat out into the hot reservoir. But there has to be work that travels in order for that process to work. So the work is equal to QH minus QC. And an example of this is kind of an old style window air conditioner where the plug where it's plugged in is what provides the work in, and the heat pump is in the air conditioning unit, causing the heat to be removed from the room and transferred to the outside. So the outside part of the air conditioner would be. And the last thing we're going to talk about very quickly is something called entropy. It's a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work. It's complete disorder randomness. So the entropy of the universe is increasing at a rapid rate. So entropy is not something that's talked about very much in this class, but we're going to just know that the term is just kind of randomness and disorder is what entropy means. So this is wrapping up our thermodynamics unit. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.